Hello everyone, welcome to the next topic of today's lecture, which is about R format instructions. So the first thing is let's take these 32 bits and split them up into fields. Specifically, we'll split them up into the different pattern that I showed below. So we'll start out with 7 bits here, then 5, 3, 5, 5, 7. Next, let's give each of these fields names, because it'll just be a little bit easier to talk about each of them. So we'll give the 7-bit field here opcode. RD is the 5-bit field, then we'll have func3 as the 3-bit field, RS1 and RS2 are each 5 bits, and finally func7 is 7 bits. So each of these fields can really be seen as unsigned integers, where like a 5-bit field can represent numbers from 0 to 31, whereas a 7-bit field could represent any number between 0 and 127, and those are just some examples of what each of these fields could do. So let's actually now break up what each of these fields does for like an R-type instruction. This is the actual format for the R-type instructions. So first we have the opcode, which is 7 bits. So this specifies the particular operation. So for example, if we have an R-type instruction, that is the opcode for it, whereas an SB-type instruction has a different opcode that you can see below right there as well. We also have the func3 and func7 fields, which combined are 10 bits. Func3 is 3 bits, aka func3. 3 bits, and func7, which means it's 7 bits long. That's how we get 10 bits total. These can be combined with the opcode to actually specify what operation we want to perform in a more precise way. So you could think about it as the opcode is like your zip code, and then the func3 and func7 are like the street address and the street name. And all of these combined will get you to the right house, which will allow you to do the operation that you want. So how many R-type or R-format instructions can we actually encode with just the single opcode that we've given you right there? Well, if we just fix this opcode, then that means we can vary the func3 and func7 fields, which means that we have 2 to the 10 possibilities, which means we have 1,024 possible R-type instructions with just this one opcode. So let's continue along with this. So we also have our register fields, which is RS1, which is the first operand, or source register 1, RS2, which is the second source register. Then we have RD, which is the destination register. So this is the register which we receive the result of our computation in. And you might have noticed that all of these are 5 bits. And I want you to quickly recall, RISC-V has 32 bits, which is why we use 5 bits for this. It's because a 5-bit field can represent 2 to the 5 values, which is equal to 32 things. And so if you interpret each as a register number, then we could represent all registers from 0 to 31. So let me now translate the ADDI instruction that I've given you here into machine code. So first thing we need to do is we need to look at what format the instruction is. So we can see we have an add here, and we see its format as R-type. So this means we're going to be using the format of R-type when we're actually translating this to machine code. So the next thing we need to do is we need to look at what are the opcodes func3 and func7 of this. So we can see this actually also on the green sheet, and it gives it to us right there. So on the left side of this, so right here, 3.3, this is the opcode, then we have func3, and then we have func7. So let's just fill in those values, because we'll need those when we're actually continuing to decode it, or to translate this instruction. So the next step is to look at the registers. So in RD, we have T0, which is equal to X5, RS1 is T1, which is X6, and T2 is X7. So we can just fill these in as hex values, because once again, these are the indexes of the registers. So those are really the IDs, essentially, of those registers. So we can just fill those in. So for this ADDI instruction, if I translate those registers, notice that I just pulled in the actual register ID, as opposed to the pseudonames that I gave you here. And that is the actual ADDI instruction that we've generated from this machine code. So now let's finally translate each of these fields into the bits with the specific number of bits that each field has. As you can see, opcode, which is this field here, even though we represented this as 2 nibbles, it's really only 7 bits, so we're only going to be putting 7 bits here. Just like func3 only has 3 bits, so we're going to only fill in 3 bits. Finally, we have all the bits we need to represent this ADDI instruction. So let's split this up, so then we can translate it into something that's a little bit more readable, such as hex. So in hex, this is the actual representation of this ADDI instruction right here. You can also represent this in decimal, which is equal to this number right here. And this is really just called a machine language instruction because it is in the language that the machine or CPU actually understands and is able to actually use to perform some operation. So say you want to do some other R-type instruction in RISC-V 32-bit. All you need to do is actually modify the func3 and func7 as all the other things stay the same. Notice the opcode is the same for all these R types. RD, RS1, and RS2 also are the exact same. And they're in the exact same locations, which means that it's really easy for the hardware to figure out what it needs to do with those types of things. The only thing it really has to do is read the func3 and func7 to determine which R-type instruction you want to perform.